In this video, we're going to learn about another way of moving money through time in a compound fashion. So I'll step off, I'll invite you to pause, copy down the notes, and then press play and I'll talk you through it. All right, so we're going to learn about an idea called compound discount. And we've seen discount in the simple setting in chapter 2, and now we can do it in the compound setting in chapter 3. All right, well, if you recall, we've already learned how to move money back in time with compound interest. So we can move a pile of money m periods back in time by multiplying that pile of money by v to the m, where v is equal to 1 over 1 plus I. Another way of saying that is I can move money back in time by dividing by 1 plus I to the m, all right? Moving it forward would mean I multiply the pile of money by 1 plus I to the m. Moving it backwards means I divide. And I've simplified the notation to just a v, all right? So in other words, the accumulated value at time t is obtained by taking the accumulated value m periods later, accumulated value at time t plus m, and multiplying it by v to the m, backing it up m units, as this time value diagram suggests. Okay, so we knew how to do that already. Well, there's another way of moving a pile of money backward via something called the compound discount rate, D. And again, if the word compound is omitted, you assume compound unless it explicitly states simple discount. Okay. Now, in a later video or in class, I'll discuss the actual meaning of what D is in terms of its actual mechanics and how it came to be. But for now, we're just going to use the formula, okay? So here's the formula. If I want to move money back in time, I'm going to take the accumulated value at time t and multiply that by 1 minus d to the tth power. And that will take the money back to time 0. So that'll give me PV sub 0, okay? So where AVT is the accumulated value at time t, PV0 is the present value, and D is the compound discount rate per unit or period of time, per year, per month, per quarter, per semi-annual, whatever it is, right? Now, I could take this formula and solve for AVT if I wish. I could solve for AVT by dividing 1 minus D to the tth power to the other side. And dividing by 1 minus d to the t is the same as multiplying by 1 minus d to the negative t, okay? So I mention that just because there's no reason to memorize both an accumulated value formula and a present value formula. One formula can do them both, all right? So don't memorize them both. All right, well, let's play with that formula with these two examples. So in the first example, Pat deposits $2,000 into an account, and the account's earning a compound discount rate of 4% per year. And what's the accumulated value after 10 years? So though I say compound discount is a way of moving money back in time, I can also use it to move money forward in time, okay? All right, so here's my time value diagram. $2,000 arrives at time 0, and I'd like to push it to time 10. And I have a 4% annual discount rate, and it's 10 years, so everything's years. Perfect. All right, well, there's the formula that I'm blocking right now. The present value is equal to the accumulated value at time 10 multiplied by 1 minus d to the 10th, all right? That's the formula I've got memorized. I can plug in the stuff I know. The present value is the $2,000. I don't know the accumulated value. My value d is 0.04, and I'm pushing it 10 years, okay? I can solve for AV10 by dividing 1 minus 0.04 to the 10th power underneath 2,000, and I get $3,008.28. So even though it's this idea of discount, it's still going to grow money as we move forward in time. All right, well, let's do example 2, which is more about dragging money back, which might feel slightly more natural given the formula. But Sean's going to receive $8,000 in 4 months and $12,000 in 6 months. We have a discount rate of 3.8% per month. Determine the present value of this set of cash flows. Now, the periods of time we're talking about are months, and our discount rate is per month. So all of our time units agree with each other. So I could have just as easily said $8,000 in 4 units of time, $12,000 in 6 units of time, and the discount rate is 3.8% per unit of time. Okay, so we're all on the same unit of time. here's the time value diagram of money I had. At time 4, I get 8,000. At time 6, I get 12,000. And I'd like to bring them both back to time 0. And there's my discount rate. All right. Well, much as we've seen before, I'm simply going to drag each pile of cash to where I want it and then add the results. So the $8,000 has to get dragged back 4 time periods. So $8,000 times 1 minus d to the 4th drags an accumulated value back 4 time periods. Plus, the 12,000 has to get dragged back 6 units of time. So 12,000 times 1 minus the d to the 6th. All right. In both cases, I'm using this formula. Accumulated value multiplied by 1 minus d to the t drags us back to the present time. So I have those 2 piles of cash dragged back, added together, and I get $16,362.69.